Hello and welcome back, everybody. Today in calculus, we will be discussing the shell method in the volumes of rotation in chapter 6. So previous to this, we talked about the disk method. We also talked about the washers method and also the rotation about a line that is not an axis. So today we will go ahead and move into something that's a little bit different, another method out of the other two. So in the AB class, this method is normally not necessary anymore. They took it out of the AP test. But nonetheless, it's still kind of nice to have because just in case, you run into something where you have to do a rotation on the AP test, you have this as an option just as a backup because sometimes the algebra or slash calculus is a little bit easier with this method than the other two. So without further ado, let's go ahead and jump into this method right here, what is known as the shell method. So here in this problem, what I would like to do is find the volume of the solid formed by rotating the region bounded by y is equal to 2x minus x squared and the x-axis about the y-axis. So the region on the right-hand side, what I'm going to do is I'm going to go ahead and rotate it about the y-axis over here. Now, normally if I rotate about the x-axis, you can see the bottom part over here, and then that's not a problem because as a result, then that's where you're going to get the disk method. But when you rotate about the y-axis, this is where it gets a little bit tricky because what's going to happen is, well, first of all, let's go ahead and draw the mirror image as we normally would. So here is what it looks like then. So here is the other part, okay? And then now afterwards, the rotation would give you something like this. So you can kind of see that there is kind of like a missing piece in the middle. So somewhat like the following over here then. Okay, so I guess it's kind of like a bunt cake then, if you would. This is going to be the end result. Now, you might think to yourself, okay, well, the way that I drew it, it definitely looks like I can use the disk method, the washer method, because you have an outer radius and then you also have an inner radius. So if I were to kind of like draw this out, this is going to be the inner part, and then this is going to be the outer part. And that right there, it seems like it's okay. But if you notice what's happening is that the inner part right here, the function that's referring to the inner part is the same as the function that is referring to the outer part, because notice over this part right here, they are referring to the same function, y is equal to 2x minus x squared. So what that means is if I do something like pi r squared minus pi r squared, where you have the bigger circle minus the smaller circle, that's not going to work out because if they're both the same equation, this is going to net me equal to 0. So the washer method in conclusion doesn't quite work here. So that doesn't quite work then. Now there's another way you can actually technically use the washers method, and that's by splitting it. So that is going to be from the interval from 0 to 1, and then adding it with the union with the interval from 1 to 2. But that's still going to be a lot of work. So we want to try to avoid doing all that extra work if possible. So here is where the shell method comes in. Now, instead of looking at these cross sections as washers, because we could look at it this way, but I'm going to go ahead and do another trick to this. I'm going to go ahead and introduce another type of cross section to this. Let's say that our cross section is going to be this cylindrical shell that I'm creating right now inside this region then, or in this volume. So this cylindrical shell is basically kind of like a, I guess kind of like a cup in a sense, right? So this is going to be one of the cross section. And if I go out a little bit further, I can see that I can create another cross section that is exactly like it. So here is another cylinder, right? Which is going to be similar to the one that I created, but you can see that it's going to be bigger. And then just draw one more for a good measure. We can go outside over here. And then you can see that there's definitely another cylindrical shell that looks like it. All of these guys are basically kind of like, toilet rolls because, they're kind of like getting bigger and bigger and bigger. And then until when you add them all up, that's going to give you your total volume. But anyhow, let's go ahead and take one of those cylindrical shells. Let's go ahead and take the one that we just created at the very beginning. Okay, and let's go ahead and see what we can do with it so we can figure out how to find the volume then. So here's the cylindrical shell, and just like all the cross sections that we've created so far, there's always going to be a thickness to it. So that is what the shell is going to look like then. Okay, now what I'm going to do is I'm going to take the shell and I'm going to go ahead and kind of like, take a scissor and then cut it. So then as a result, you are actually going to get a rectangle from the shell. So the rectangle would look something like this. I would like to find the volume of that small little piece. So then from there, we can go ahead and set up integral then. Now, the thickness to this shell, because if you can see the expansion of these shells, right, it's getting, they're stacked horizontally. So it's kind of like, that Russian doll, I forgot what's the name of it, but it's the same idea where you kind of put one inside the other. So what that means is that the thickness is going to be equal to delta x, right? Because again, they're stacked horizontally from each other. Now, let's go ahead and find out the rest of the characteristics. If you look at the vertical distance, that is definitely going to be y, because that is always going to be my vertical distance. And my horizontal length of this shell right here, now this length up on top, that is the same as the circumference of the cylinder, because you're going to cut it straight down vertically. So what that means is this is going to be equal to 2 pi r, where r is going to be x then, because it's, again, the circumference. So that means the volume of this small little space, volume of this small little shell right here is going to be equal to 2 pi xy multiplied by delta x. And that right there is going to be a small little slice. Now, if I take the total volume, then that means, again, it's going to be the summation of every single one of those small little slices, put them all together. So that's where, again, your integral is going to come in. So it's going to be the integral, and we're going to go ahead and start with 2 pi, and then we have xy, and then we have dx. Your boundary, because it's x, now this is where you have to be very careful. You are actually going to go from 0 all the way to 2, because a lot of people are thinking, okay, well, we're going to go from -2 to 2, but that's wrong. Remember, whenever you have a cylinder, it goes in both directions, left and right. So that means that when you're taking the cylinder at x equals to 1, then that expands all the way to the left-hand side. So what that means is that it's kind of like your boundary is from the very middle to the very outside. So that is going to be from 0 to 1 instead. Okay, oh, sorry, 0 to 2 instead. Okay, so you don't have to go from like, full end to the other end. It's just from the middle, from the inside out. Okay, so that's probably the best way to explain it. But there you go. That's going to be my shell method. And you'll notice that, we have a y right here, normally just something that we need to replace. And that replacement, that's where my equation is going to come in. So let's go ahead and make that replacement then. So 2 pi integral from 0 to 2, x multiplied by 2x minus x squared dx. So if we can solve for this integral, using FTC2, then we have our volume that we need then. So this, I guess, what we can do is multiply everything out. So 2 pi integral from 0 to 2, 2x squared minus x cubed dx. And then now we take the antiderivative. So this will give us 2/3 x to the third minus 1/4 x to the fourth, boundary from 0 to 2. Go ahead and plug in the upper bound minus the lower bound. So 2 pi, I'm going to go ahead and keep it outside. For the upper bound, when we plug in 2, we're going to get 16 over 3 minus, plug in 2, we're going to get 16 divided by 4, so that's going to be 4 then. Minus a bunch of zeros, so that's easy enough. So let's see, if we put it all together, that is going to be equal to 5 and 1/3. So that means if I subtract 4 from it, then that's going to be equal to 4 and 1/3, sorry, 1 and 1/3. So that is going to give me 4/3 then as a result. Multiply that by the 2 pi by the outside. So your final volume is going to be 8 pi divided by 3. All right, well, there you go. That is going to be my shell method then, okay? Now, as I was saying earlier, what we can do is we can actually take one of the previous problems that we did with the disk method or the washer method and apply the shell method to it because, it's just another variation of solving for the volume. You pick whichever one is going to be easier. So here's an example of a problem that we did in the past where you could use either one. In this case, what I would want you to do is the following then. I want you to verify the volume of the sphere with a radius of r is going to be 4/3 pi r cubed via the shell method. So if we're thinking about using the disk method to do this, here's what I'm really asking for you to do, right? Here we have an equation of x squared plus y squared. Oops, using the wrong pen over here. So let me go ahead and kind of erase that. We have an equation of x squared plus y squared is equal to r squared. Now, technically, in this case, r is equal to 1, but let's just go ahead and say that 1 is the arbitrary radius. So we're just going to go ahead and say that it's some other number. It could be 4, it could be 5, or whatever it is, okay? If I want to find the volume of this sphere, what I would do is I could create a disk method, because here I can go ahead and create a disk that looks like this, right? So you can see the sphere that I'm asking for, the volume of the sphere that I'm looking for, is basically the rotation of this circle about the x-axis. Or you could say about the y-axis. Either one, it's going to give you the formula. So if I were to just go ahead and show using the disk method, right, that is going to be the integral from, looks like it's going to be negative r to r, and then it's supposed to be pi y squared dx, because y is supposed to be the radius over here, okay? So that is going to be the reason why it's pi y squared then. And just to make it a little bit easier, I guess we can go ahead and say from 0 to r, because it's symmetric, multiply by 2, and I'm going to go ahead and take the pi and put it outside. Y squared, that gets replaced by the equation of r squared minus x squared, because we're referring to this circle that's over here. Taking the antiderivative then, so 2 pi, we have r squared times x minus 1/3 r to the cube, because remember our variable is supposed to be x and r is supposed to be a constant, from 0 to r. Plugging in what we have r to the third minus 1/3 r to the third. So let's see here. This gives us 2/3 r to the third multiplied by 2 pi. And as we said, that's going to be equal to 4/3 pi r cubed. So this is using the disk method. But now what I want to do is I want to go ahead and verify that I'm going to get the same answer using the washer method. Sorry, not the washer method, but the shell method. So first of all, you have to think about, okay, well, how are you going to build these shells? Hopefully you guys can kind of see it. The shell that you're looking at is going to be something like the following then. So here is going to be one possible shell in this case, okay? Again, you know, your rotation doesn't matter. You can rotate about the x-axis or you can rotate about the y-axis because it's still going to come out to be spheres. Okay, so that is going to be my shell in this case. Let me go ahead and erase all of these guys over here just so that we can make a little bit of room. So this time, let's go ahead and see if we can come up with the same answer. And if it doesn't come out to be the same answer, well, it's going to be shame on me then in this part, okay? So first, we're going to go ahead and take that shell, and we're going to draw it, so then that way you can see that it's going to be a rectangle, just like we did. We're going to take that shell, cut it vertically to see what is the volume then, okay? So there is going to be a thickness to this. And since these shells are stacked horizontally once again, because, you know, if you want, you can draw another one. You can see it over here, okay? So that's why it's going to be all horizontal. It's going to be dx in this case then, okay? So the thickness is going to be delta x. Now, the height, right, the height of it, it goes from the top to the bottom. So that means that it's not just y, be very careful, because y only goes from here to here. Well, if it goes from the very top to the very bottom over here, there's another y on the bottom, which means that the height is going to be 2y then, okay? Again, keeping in mind that wherever the cross-section is, we're going to go ahead and denote that point where it touches the curve, x comma y then. Okay, so you can see how y is never going to be negative because we're choosing something that's in quadrant 1 just to make it a little bit safer. All right, as for the top part, the width, that is again going to be the circumference of this shell over here. So that is, once again, it's going to be 2 pi multiplied by r, which in this case, once again, it's going to be x then. So put it all together. So the volume of this little slab, this is going to be equal to 4 pi xy multiplied by delta x. The volume total is then equal to the summation of every single one of those slabs then, and that will then give us the volume of the sphere that we want. So let's see, integral 4 pi goes outside. We have xy, and then that delta x becomes dx. My boundary, remember again, is from the middle to the outside, right? Not from the far left to the far right. So that means it's going to be from 0, that's where your first shell is going to be created because it's in the middle, all the way to 1, which is on the right-hand side. Now, if you're wondering, can I go to the left from 0 to -1? The answer is, well, technically you kind of can, but then that means you're going to have to swap the integral because from 0 to -1 is kind of like the reverse of it, right? We need to go from a lower number to an upper number. Okay, but anyhow, if we solve for this, we're pretty much good to go. So let's see, 4 pi integral from 0 to 1, x, and then y gets replaced by the equation of the circle. So that is going to be x squared plus y squared is equal to r squared. Oh, I'm sorry, it's not r, it's actually 1 in this case, right? So it's from 0 to r, 0 to r. So that means that y is equal to the square root of r squared minus x squared. So we have r squared minus x squared dx. If I can solve for this integral, then that means that's going to be my answer. So what I'm seeing in this case is we're going to use a u substitution. Let u equal to the inside part, r squared minus x squared. So du is equal to negative 2x dx. So let's see. So then that means that x dx, which is what I have in the equation, is going to be equal to negative du over 2. So going back to my equation, I'm going to change everything that's in terms of x into terms of u. So the 4 pi stays the same. The boundary, if x is equal to 0, then u is going to be equal to, looks like it's r squared in this case, right? But whereas if the top part, if x is equal to r, then u is going to be equal to 0. Then we have the x dx part gets replaced by du over negative 2. So that works out nicely because I don't like the fact that it's going from r squared to 0. Then we have the square root of u over here. So let's go ahead and kind of swap some stuff around. We have the 4 pi still. I'm going to change the boundary from 0 to r squared, which extracts out a negative. And then that negative would then cancel out with the negative that's over here on the bottom. So these guys are going to go away. So now we have 2 pi. Let's take the antiderivative. U to the power of 3/2 multiplied by 2/3 and then boundary from 0 to r squared. Plugging in what we have for the values because we don't have to go back and change it back into terms of x. So we have 4 pi over 3 multiplied by r squared. So that is going to be what u gets replaced by, raised to the power of 3/2. And then minus the lower bound, which is 0. So we don't have to worry about that. But you can see how the 2 and the 1/2 cancels out. So once again, the volume is equal to 4/3 r to the 3rd power then. Okay. So in this scenario, you can see how the shell method works, and then you also saw how the disk method work. Usually, you're given the choice as to which one you want, and in this case, the disk method, the integration was a little bit easier than the shell method, but it's not always going to be that case because you just have to kind of like see or intuition, or maybe just kind of write it out to see which one's easier sometimes. Okay, here, let's go ahead and deal with this last one right here. This last one is going to be set up an integral for the region y is equal to 4 minus x squared. I want to set up the integral for the following. Okay, so the region that I have is y is equal to 4 minus x squared and also the x-axis, so you can see on the right-hand side. What I would like to do is rotate that region about the line y is equal to -2. So over here, I can kind of draw that just so that you can see how it looks like. First, what I'm going to do is I'm going to go ahead and introduce that line of rotation. Okay, so that is going to be my center of axes then. So there is going to be a little part over here on the bottom. Not a little part, but it's actually going to be a big part. Okay, so this is what the symmetric part looks like. It's going to be something like this down here. Okay. Then as a result, we're going to go ahead and do a rotation. So then that means that you're going to get something that looks like the following then. Okay, So you can kind of see that this is going to be my cross section. And this cross section over here is basically screaming out using the washer method, okay? But once again, we're in the section where you're going to be using the shell method, or I'm trying to teach you the shell method. So let's probably go ahead with that, just so that you can see how that works out. Here, well, you know what? Let's just do both. Okay? So let's just say I'm going to go ahead and set up the washer method, okay? Because all they're asking for is just to set up, and that's what happens in a lot of the AP test problems. They just ask you to set it up, but don't worry about integrating, okay? Now, for this washer, let's see here. We need to look at the inner radius and then minus the outer radius. The inner radius, well, first of all, let's go ahead and take that point where it touches the curve once again, the washer, and call it x comma y, okay? The inner radius, you can see that it's this distance, and it's always going to be the same. It looks like it's always going to be 2. So that means in terms of my setup, where I have pi capital R squared minus pi lower r squared, and then in this case, the thickness is going to be delta x right here. This lowercase r, that is going to be equal to 2. Okay, so that is always going to be fixed. And since the radius is a distance, we always want this to be positive. We shouldn't want this to be negative. But whereas for the upper or the bigger radius, that is going to be the distance from where the point is, right, all the way down to the center of, to the central axis right here. Well, you can see, as we said earlier, this part is going to be 2. And then this part vertically, well, since it goes up to that point, that has to be y. So then that tells me that r, the capital R, the outer radius, is going to be y plus 2, where y is in reference to this equation. Let's see. That's going to be my that's going to be my washer right there. And the summation of every single one of those washers will then give me the total volume. So in this case, let's see, my integral. Let's see, we're going to go from -2 to 2, and then we're going to go ahead and take the pi outside. Capital R squared, that is supposed to be y plus 2 quantity squared, and then minus, for the lowercase r, that's going to be equal to 2, and that's going to get squared. And then you have dx. Well, it looks like the final thing we have to do is replace that y with the equation. So that means we're going to go ahead and change it. So it's going to be 4 minus x squared plus 2 inside squared minus 4. And then we have dx. And let's go ahead and change that boundaries too, just for the sake of symmetry in this case. I'm going to say from 0 to 2 and put a 2 pi outside. So this would be one integral. That could be our answer according to the washer's method. All right. Now, what we're going to do now is going to go ahead and show using this method, or set up using this method. Let me go ahead and erase some of this stuff over here just to give it a little bit room. Okay. So let me see. Can I erase this? I'm going to erase this right here. And then let's see. Can I erase a little bit more without having to kill anything else? No, I don't think I can, unfortunately. All right. So let's see here. Actually, you know what? I'm going to have to erase this too, unfortunately, because that's where my shell is going to, yeah, we're going to have to create a shell, and we're going to have to be able to see it. Okay, so the question is, where's that shell then? In this case, my shell that I'm going to create will look something like the following. Let me go ahead and use black in here, just so you can see it better. So this part right here, that's going to be one part of the shell. And then on the bottom is going to be another part of the shell, right? And then that is going to be our cross section right there, according to the shell method, okay? So that is going to be our big cylinder, okay? We're going to have a big cylinder like this. Okay, so we're going to go ahead and take that out and then see if we can kind of like, figure out what part is what, okay? So that is going to be our shell right there. Now, these shells are going to be stacked vertically in this case. So that means that our thickness in this situation is going to be delta y. So that is going to be the first part. So that is going to be the thickness, okay? Okay. Let's take care of this horizontal length. In our picture, that horizontal length is basically the same thing as this right here. X is the distance from that point to the y-axis. So that means that since there are two of them, so I'm going to go ahead and say that that's equal to 2x over here then. All right, now we're going to go ahead and figure out what is this part over here. Well, that is supposed to be the circumference of the circle that I'm going to create. So let me go ahead and draw the axis of rotation, which is located right here in the center, and that is supposed to be y is equal to -2. If you remember, right, vertically, y is supposed to be the distance from that point to only the x-axis. So that's going to be y. My radius that I'm looking for extends beyond that. It's going to be from here, the axis of rotation, all the way to that point. So there's an extra 2 that's over here. So what I'm saying is that the radius that we're looking at, that is going to be y plus 2. So then that means that if I were looking at this as a circumference, then that means that this piece, the circumference, okay, is going to be 2 pi multiplied by y plus 2. All right, so let's go ahead and put it all together. The volume of the slab, or the volume of the cylinder, is going to be 2 pi y plus 2 multiplied by 2x, and then we have a thickness of delta y. The summation of every single one of those slabs would then give us the total volume. So that's going to be the summation of that thing over here. Okay, so we're just going to kind of repeat it. So that's where the integral is going to show up then. So let's go ahead and write that out. I have 2 pi and 2x, so I'm going to write outside 4 pi. Integral, we have y plus 2, the x has to stay inside. We have dy over here. My boundary is going to be from the middle all the way to the outside, from the inside all the way out. Now the inside middle is technically at y is equal to -2, but you'll notice vertically there is nothing. It's empty. It's hollow from -2 to 0, so we don't actually have to start from the middle all the way outside. Instead, we're going to start from 0 all the way out to 4, because that's where you're going to start creating your first shell at 0, y is equal to 0, all the way to your last shell, which is at y is equal to 4. So that is going to be my boundary, okay? And the last thing I'm going to do is I'm going to go ahead and take x and replace it back with the original equation. And you can see how this right here is going to be a little bit nasty looking, because we're going to have to, do a little bit of algebra. Y is equal to 4 minus x squared. So it looks like we're going to have x squared is equal to 4 minus y. So x is equal to the square root of 4 minus y. So my final equation is going to be 4 pi integral from 0 to 4 y plus 2 multiplied by the square root of 4 minus y dy. So if we can solve for this integral, then that is going to give us our answer as well. But for this one, we're just going to have to set it up. All right, so thank you so much for watching. I will see you guys next time, and hopefully you picked up something from all of this. All right, have a good one.